Good afternoon. This is Schweitzer. We're going to run through a couple of problems here just to prep you for our test. It's got a little bit of everything here. All right, so what do we got here? It says energy equals Q plus W. Now, some of the stuff we covered to different extents, different times, but this essentially is a conservation of energy problem here. And looking at here is total energy is conserved. So all energy comes in many forms. So Q Q stands for heat. And then sometimes, like when you drive your car to school, your car gives off actually several types of. It's not a very good car. There we go. Still not good. So it gives off heat, and you'll know it goes off a lot of heat. But it also produces kinetic energy and it produces potential energy, which means that you could maybe take your car and drive it to the top of a hill. And then if you parked it there, then you walked away, and there's a possibility that car could roll down the hill all without you doing anything, even stirring the car. So all these are types of energy, and this guy here is just involves kinetic energy and potential energy, and there's other ones too, but this is a lot of it. So this just means conservation of total energy. So which of the following is true about basic conservation of energy? All energy from a car driving to school can be represented as either kinetic energy or potential energy. That's no, because we also have heat. An expanding gas from an inflating car tire um, and the car into bringing the car into the air, the example of work, then that is true. Just lifting something up in the air requires an input of energy, so technically that's a yes. If you take and pump a car tire up, it will lift the car up. If Q is negative, then work will have to be positive. Um, in this case, that's not necessarily true either. This is just heat. This is work. Two separate things. Um, Overall, these together have to equal the energy before, but these don't have to be equal necessarily. So that would be no. And that problem's got a little bit of quirk to it that may not be as suitable for our test as possible, but just some ideas. The block is placed in a block is placed into a sample of water, and the block increases 10 degrees, which the following is true. So let's draw a picture of that. We have a beaker, and we took a block, and we dropped the block into some water, and the block actually got warmer by 10 degrees. So energy entered the block. The water was actually hotter than the block. Yes. The water and the block changed the same degrees temperature. We don't know that for sure. We need to do that. We need Q equals mass times change in temperature times heat. They don't have the same mass. They don't have the same heat. So we don't know that this is the same. The energy lost by the water is gained by the block. Yes. So we're looking at 1 and 3. Okay, next one, which the following is true when 23 grams of ethanol is vaporized according to the process above. Now you'll notice here as we get started here, 23 grams and 46, we only have 1/2 mole of this stuff. Alright, the process is endothermic. That's a yes. Anytime you're putting energy on the left hand side or energy is entering the system, that's endothermic. Ethanol will gain 16.5 kilojoules of energy, and that's exactly 1/2 of that, so yes. The temperature will not increase during this process, and the answer is actually yes as well. Here's the rationale from 3. We're doing a phase change, and we know that during a phase change, alright, from a liquid to a gas, energy is being put into the system. Okay. Does that mean we have to raise in temperature? And answer is no. Just because we add energy to a system doesn't mean that system has to get hotter. It can change that energy into other forms. In this case, into bond energy. It's using energy to form bonds or break bonds or do different things. During a phase change, the temperature remains constant. Okay, all three is the answer here. All right, good thinker question there. Which of the following is true concerning a chemical reaction? Okay. All right, now these are the delta H's for this stuff, and zero energy is involved in the oxygen-hydrogen bond. Okay, that's no, that's that's not true. This is zero here, but this is delta H of formations, and we know that that's just a relative scale. All right. The energy needed to break a bonds is smaller than the energy needed to release bonds. So this thing is going to be exothermic. So the delta H is equal to the bonds broken. Sorry, delta H is the bonds broken minus bonds formed. And this guy is negative, which means that this one must have been larger than this one. So the bonds broken, we had to put energy into break bonds, and we got energy released when we formed them, and we released a lot more than we did breaking them. So that's why it's exothermic. The energy needed to break bonds is smaller than energy smaller than energy released from when bonds are formed. That is yes. Breaking bonds always releases energy. No. When we form bonds, release energy. That's a big misconception there. Good question. All right. Copper cup is used for serving drinks. Heat capacity is joules per 34 joules per degree Celsius. Now you notice that here. It's really important to notice these units. Kids don't always look at this. It's just literally 34 joules for every degree Celsius. That's it. The mass of the cup is never going to change. So they just do a heat capacity instead. It's a simplified version of a specific heat. The quantity of energy needed to raise 1 degree Celsius. The cup is holding 100 grams of water. The water is holding 100 grams of water and is poured into the cup. Okay, this action causes the cup to be cooled by 50 degrees. How much energy did the cup gain or lose? Okay, so it's just going to be 50 degrees, and then get rid of degrees and go to joules. Every 1 degree Celsius is 34 degrees. All right, 50 times 34, 1700 joules of energy. All right, student hypothesis. The cup cooled 50 degrees, so the water must have warmed 50 degrees. Just to nullify this concept. It is nullifying. Again, we know that the energy is the same. So as the Q equals mass times change in temperature times heat, this would be, let's say, for the cup. But then for the water, okay, is Q equals mass times change in temperature times the heat. Then these two here are the same, but the masses aren't the same. The change in temperature heats aren't the same, so the temperatures are the same. So, not true. All right. Due to different specific heats and masses, we don't know if the change in temperature is equal. All right. We'll stop there for today. Thank you.